Okay, so this is serverless data updates in ArcGIS Online and Enterprise. I'm Nick Fink. I'm a senior geospatial system engineer with New Lake Technologies.
And I'm Rob Pitts, a program manager with New Lake Technologies. Okay, so New Light Technologies, or NLT, is an integrated IT and geospatial services consultancy based in Washington, D.C., offering a range of cloud and enterprise IT, agile software development, cybersecurity, data science, and geospatial and research services for customers in government, nonprofit, and private sectors. One of the major focuses of our work over the years has been developing solutions to improve integration, interoperability, and data exchange between enterprise systems, including, of course, Esri. And with all the various data formats, software platforms, security protocols, and use cases across large organizations, this can be a real challenge that requires creative solutions. And with the dizzying advancement of the public cloud, there are a growing number of unique tools and services that can be leveraged to help with these problems to keep data flowing. And today we're going to discuss our approach to using several cloud-native serverless technologies to facilitate automating data updates in ArcGIS Online and Enterprise. Okay, next slide.
So the problem here, have you ever come across an API that has spatial data, lat longs, XY coordinates, but it's not really a spatially compatible format, so it's not, it's not an Esri REST, it's not OGC compliant, just something where the data doesn't work with ArcGIS out of the box. So you need to do some sort of processing of the data. And this is usually something that's be very useful to have because it's, near real time. It might not be continuously streaming. It might not be updating every second, but, certainly every 5-10 minutes, or even something that's updating daily or weekly that you just need to get, and you just need to get it into your WebGIS. So there are existing solutions. Obviously, Esri's done a great job of engineering some very robust platforms, and those platforms would be useless without data. And, a lot of data is useless if you can't update it. So, our workflow here isn't a total replacement for these workflows. It's just something new and sort of advanced that we've been working on for a while now. I'm sure many of you are familiar with updating data in ArcGIS Online or your portal, or even an ArcGIS REST service through ArcGIS Server, through staging an MXD and more recently an APRX file in ArcGIS Desktop and ArcGIS Pro, respectively. And these work great. They use service definitions to update what's happening in the portal. They work really, really well for large amounts of data. Really, if you have millions of points or even hundreds of thousands of points, it's really hard to beat a service definition to update your data. And this solution doesn't compete with that in terms of large data updates, but it's a new way that's might take some of the pressure off of the old ways of doing things. And then, of course, when you have streaming data, you can have GeoEvent Server and more recently ArcGIS Velocity, both great products for streaming large volumes of data. We have many clients that are using these. And they're great for real time and they're great for analysis. And so that's what currently exists in the market. That being said, these existing solutions do have some drawbacks. MXD and APRX files are, they need to be manually staged. They need to be maintained. You have to make sure that they work with whatever version of desktop software you happen to be working with. That's specific to MXDs usually. And with those come the need for physical or virtual servers or desktop towers, as many people are using, to run update workflows with ArcPy or GeoEvent Server. So you're not just updating data and maintaining ArcMap, you're doing system patches, you're making sure that your servers are always up and protected, and there's a lot of baggage that goes along with either a physical server or a virtual machine. And even when you look at ArcGIS Velocity, which is a total SaaS application, seems to be a great product. You might not need continuous streaming capabilities, like I said earlier. You could have a data set that just requires every half hour, every day, every week, every month. And you might not want to stand up an entire system or workflow that's geared towards streaming data if you don't need that capability. So at this point, many people watching, I'm sure you're familiar with the ArcGIS Python API. It's really great to interact with Esri portals programmatically. So a lot of people are using it for analysis or, updating data, or I'm sure some people are out there experimenting with building web maps and story maps and things like that. It's a really powerful tool. It's amazing. I remember, a few years back before the Python API became widely used, trying to figure out API calls through the documentation. And this takes a lot of the headache out of that, and it makes it super simple to manage and interact with your portal. We're using it to great effect here, basically because, it doesn't require that same licensing model that ArcPy uses. So what we can do is we can package it up outside a Windows environment and authenticate through our portal credentials, which means we can take this and we can put it into a Linux environment, such as, an AWS Lambda we use. So an AWS Lambda is Amazon's serverless function environment that will allow us to build out and run jobs without having to build any infrastructure. And what else is great about this is that the Python API actually has a GitHub repo where, if you find a bug, you can actually dig into the code in the Python API, find where the bug is, go to the GitHub repo, create a bug ticket. And the development team are usually really quick to respond. They're really good about implementing solutions. And it's just, I find it, really great to have that dialogue with the development team when I find a bug and, I'm trying to get it resolved.
So what is serverless? Well, as the name implies, it's basically on-demand computing and software services provided by the cloud directly that don't require procurement, configuration, or interaction with servers and operating systems and the like. So this provides developers the ability to use those services without any setup or ongoing maintenance, which is a huge time and cost saver. So if you go to the next slide, this shows kind of the evolution in computing architectures from physical servers in the lower left to serverless in the upper right. Physical servers, which provide the whole bare metal computer upon which, you're adding an operating system and software and everything, evolved into virtual machines or VMs, which is basically infrastructure as a service, allowing easy deployment and replication of servers, of course, but does require the maintenance of each one. Containerization technology advances this virtualization from the machine level to the application level, allowing users to basically ignore the servers and the OSs and work directly to build and package up modular applications that can be deployed really anywhere, though orchestration of containers does require some overhead and maintenance. And then to serverless, which advances this even further from the application level to the function level and provides basically direct access to services that require no server or OS or application configuration or maintenance at all. So this makes it extremely easy now to deploy scripts or code without having to set up or maintain all the underlying infrastructure and platforms and applications. So for some uses, including a growing number in the geospatial industry, this is a major advantage, obviously. Okay, next slide. So here are basically a list of some of the benefits. I don't know, Nick, if you want to, explain some of these from your perspective.
Sure. So, what's really great about serverless is you're not locked into one service provider. So multiple cloud providers are doing serverless. Sure, you've got AWS, but you've also got Microsoft Azure, Google's cloud platform, Alibaba, and they're allowing you to deploy a wide variety of runtimes. So Node.js, Python, there's a ton of stuff that you can deploy serverlessly. Obviously, like Rob said, there's less maintenance. So you don't have any physical maintenance because you're not maintaining a data center. You don't have any OS level maintenance because you're, you aren't using this at an operating system level. You're designing and deploying into one type of operating system, and you design your function for that, and you deploy. Networking is at a minimum. You can set up some networking if you really feel that way, but you don't need to add any networking to your function jobs if you don't need to. It allows really fine-grained control of the workflows. A lot of these you can tell it, you can use this much memory, you can use this much time before it times out. So it really allows you fine-grained control, and it allows you to distribute the jobs because your workflows aren't fighting for a finite amount of resources. So let's say you have a server that has 4 cores, and you have several jobs that need to run. You're restricted by those finite resources, whether it's compute or memory or network. These are totally distributed jobs. One Lambda in this scenario doesn't affect another. We can run as many as honestly Amazon will allow us to run at one time, and they're totally isolated. And those resources are only consumed in runtime. So that means you're not paying for a VM to be sitting there on. You're not paying you're not paying for cooling or electricity for any physical machine you might have in your data center. These functions only run, or they only consume compute at runtime. So in our scenario, we're running triggers that say run every 5 minutes, run every 30 minutes, run the first Sunday of every month at 8 a.m. Because we're not paying for that overhead of having it sitting there always on waiting, it's an extremely low cost model because it only runs and you only have to pay for resources consumed at runtime. Another great thing here with serverless is it's programmatically deployable via infrastructure as code. And what this means is that you can take and you can write some code, whether it is through the Python library Terraform for interacting with the rules for CloudFormation to create a CloudFormation template, or it is HashiCorp's Terraform, or any of those. It makes it really, really easy to deploy your infrastructure literally as code. There's no manual process involved. which dramatically cuts down on user error, fatigue. Anybody who's ever had to deploy the same thing 20 times in a row, if it's even minorly complex, tedium will set in, mistakes happen, and infrastructure as code helps to rapidly cut down on that. And it's a really, really great benefit of going serverless.
Yeah. One other thing, Nick, on that is, just the speed to deployment time, being able to sort of deploy code and get right to that part of it without having to, build and set up a machine or the software and servers that are required, even application servers, middleware, whatever, to deploy different things. I think this is a huge benefit. It just allows developers to immediately begin working on a solution and deploying it out there, testing it, whatever, without all the time that goes into just getting to that point. And so I think time to development is another huge benefit.
Thanks, Rob. So this is our first use case. It's the one we'll be addressing in our demonstration today, where a government entity has released their data publicly, but maybe spatial isn't a big enough footprint at their agency where they wouldn't think, well, let's release this in a spatial format. So they go and they release a API. It's JSON. It's programmatic. It's structured. It's got latitude and longitude attached to it, but it's not in an Esri REST format. It's not in WFS. It's just JSON. So the solution here is to take a Python script. You grab your JSON, you convert it to a CSV with pandas, and then you upload to ArcGIS Online, where ArcGIS Online will recognize it as a CSV. It does a really, really good job of locating the spatial pieces of the data and creating a feature service out of it. Use case 2 is similar, but in this case, we have a cloud-hosted RDBMS. So let's call it, SQL Server that an agency has a production database in. They have a table. It's got XYs involved in their table. But you'd like to kind of skip over the whole part where you grab it, export it, put it into a geodatabase of some sort, stage the MXD, stage the APRX file, and then push to ArcGIS Online. But to do it this way, where you use a Python script in a Lambda to query a database that's maybe hosted in AWS's RDS, relational database service, and grab the data there, create a CSV of it, and upload to ArcGIS Online as a feature service. That's a really powerful cloud native way of achieving the same results as the old way of grabbing the data, putting it into a geodatabase, staging an MXD, and then publishing. We're cutting out steps here, and by removing steps, we're removing complexity, we're saving time, and no GIS person, maybe me and Rob, want to spend a ton of their time staging data and running data updates and maintenance. A lot of GIS people, they want the data, they want it in their platform that they've invested in, and they want to start doing analytics, and that's totally valid. And this workflow is a way to try and take some of the pain out of getting data into your platform.
Yeah, that's a great point.
So our solution here is, we want to simplify the ETL by bypassing the staging and automate the publishing as much as we can, and we want to automate updates as much as we can. It's also got the benefits of It's cloud native because we're running all of this in the cloud. There's no VMs, there's no software, there's no OS patches, it's just build it for Linux and get it running and let it do its thing. It's incredibly lightweight, incredibly low cost. I think the code that I use for the Lambda is 46 megabytes total. So it's a small footprint. It's a much smaller footprint than having to maintain even a desktop tower. So you can kind of see here our quick little diagram where, data from an API goes into a Lambda with the ArcGIS Python API that's kicked off by an event bridge trigger. It produces either a GeoJSON or a CSV, and it puts that data into your ArcGIS portal. So now I'm going to do a quick demonstration here with some Python that I've written. So our first script here, we're going to auto-publish the data. You can see here, this is my test user's account. It doesn't own any content. So there's no trickery. So what we're going to do is we're going to run auto-publish here. So it's going to grab some data from the Southeastern Pennsylvania Transportation Authority's TrainView API, which shows commuter trains and their locations. So now we'll refresh the page. You can see we've created a folder called My Test Folder, and we now have a feature layer. So that was very fast, ran in seconds. So you can see what we've done here. We gave it a title, we gave it a summary, we gave it a description. This all happened in the script. We look at the data table. So we've got all the information from the API we just created. If we go to the visualization tab, we've got dots on a map. It's that simple. It's really, really fast, really, really simple.
Right. So Nick, it's taken data in from an API hosted by SEPTA and automatically published that to your ArcGIS Online account. Is that right?
Right. So if we look at the original data source here, you can see this is just JSON. We've got a latitude and longitude, and then we've got the information about the train. And that gets converted into a CSV, which then gets loaded here with all the information in a really nice, viewable way. We come to the map. Obviously, there's all our information. But that's great. Without the data updating, really, what good is it? So we've got another script here. We're going to take the item ID, add it to our variables in this script. So what just happened was a cloud formation template was created. Creates a YAML file with all of our variables and our infrastructure. So then we go over here to our command prompt, and I have some commands already ready to go here. So what we're going to do all right, for some reason this is giving me some trouble. So what we're doing here is we're going to call the AWS CLI, command line interface, and we're going to have it build a CloudFormation stack based on the template we just created. One small typo, that always trips you up. All right, so we can see it's running now. We're waiting for a change set to be created. So if we go over to our AWS console here, we can see our Dev Summit is being created. And you can see the create in progress. So this is going to take about 2 minutes to run because we're building on the fly. But you know, this is one way just to make sure everything is done correctly every single time.
Gotcha. Hey, Nick, can you describe the role that a YAML file plays in this? What is a YAML file and what do you
So
use
YAML is like a more readable JSON. So you can see here, you know, it's giving us our resources, you know, my awesome API test. So this is building out the Lambda here. You know, here's our environmental variables that are going into it. You know, here's the function name, here's the handler. So, you know, what our script is called. You know, it's creating permissions on the fly. It's creating the role for your Lambda on the fly in AWS. It's creating rules for the CloudWatch event. So our rule here is, you know, we're creating an event that kicks off this script every 5 minutes. So you can see we're kind of chugging along here where most of our stuff is done. Yeah, so we should be completed here. Create complete, excellent. So did it update immediately? All right, it hasn't updated yet, but what we can do is we can go over to our Lambda that we just created. And we can create a test event. So if you look up here, you can see in the upper right-hand corner, you can see that last updated at 4:01 when we created the feature service. So we're going to run a test here. Hopefully this works. It's always a crapshoot when you do things live. All right, so the execution succeeded. It took around 11 seconds. So we're only getting billed for 11 seconds. We're only getting billed for 184 megabytes used. We come back here. Let's refresh our page. All right, great. So now we see that it updated about half a minute ago. We now have one more record than we did before. And it may be difficult to tell, but some of our dots have moved. So with our demonstration done.
Yeah, it worked. That's great.
It worked. So that's always small blessings when something works live. So limitations and considerations. This works. We know it works. We just did a live demonstration that it works. It's got to have drawbacks, right? Absolutely. I'm never going to hide them. So in an AWS Lambda for this particular workflow, we're limited to 512 megabytes. That's about half a gig in our temporary workspace. So what does that mean? That means that our temporary file cannot exceed 512 megabytes. So this is not going to work for massive data sets. It's not going to typically work for streaming because, as you just saw, even a data set this small, 26 points, it takes around 11 seconds to run. So it's just probably too much latency for any data that needs to be streamed, because we're doing overwrites and not appends or updates. The other problem here is that we're doing a 15-minute timeout because that's the maximum amount of time that a Lambda can live for. If you hit that timeout limit, if it completes at 14 minutes and 59 seconds, your job will complete. At 15 minutes and 0 seconds, the job will shut down and your function will not complete. The other limitation consideration here is, a lot of groups maybe already are pretty invested in their current workflows, and making those changes is time consuming, and that's money that needs to be spent if you're going to update your workflow to this. So we don't want to minimize that consideration.
Yeah, it does take some sort of rethinking and new development here to make this work. But if there are opportunities where it makes sense to reimagine a workflow with using this kind of technology, it's a great time to implement it.
Right, and and this is very early for this workflow. This kind of thing I think might be in its infancy, and I'm excited to see how it develops going forward. So speaking of going forward, looking at future directions, this particular workflow, I'd like to expand integration with other AWS services. Like some of you who are closely paying attention might have seen me using Secrets Manager to handle my credentials. I'd like to use more of AWS's monitoring and notification tools, so SQS, SNS, to say, all right, this workflow has failed 3 times in a row. Let's fire off a text message or an email to people that might be concerned about that. So there's tons of functionality, and that's what's really great about this is, between Python and the amount of services available in the public cloud, it's really limited only by your imagination and your budget. Obviously, the public cloud tends to be a la carte, so you really do need to pay attention to what services you're using and how much you're using them. But with a good architecture, it's really, really cheap and really, really robust. I'd like to expand the Python and geoprocessing functionality. We have a developer on our team who's kind of taken this workflow and strung it together with some open source tools to do some geoprocessing, and then takes those and outputs a shapefile and puts that into ArcGIS Online for a client. It's really great to see that kind of that marriage of open source and enterprise. I firmly believe that they can live together and they can work together very well, and this process really demonstrates that. And in the future, I'd like to expand this to other cloud service providers. So obviously, during this presentation, we've been really focused on Amazon Web Services, but let's not forget that there's other providers out there. There's Microsoft Azure, there's Google Cloud Provider, there's Alibaba, and they can package and run code serverlessly as well. And there are some nuances to be worked out there. And not everybody's using AWS, and it's important to make sure that we can run this across any cloud provider, and maximize people's investment in their Esri enterprise and their ArcGIS Online, and really leverage the use of the ArcGIS Python API to make sure that they're getting the most out of the platforms that they're investing in for their location intelligence and their business intelligence.
Yeah, that's a great point, Nick. I really think this is important because, in the geospatial industry, like you were saying before, people want to get to the analytics and doing the science of geography, right? As Esri calls it. And, you know, leveraging these kinds of technologies helps that. And I think, we're going to see more use of, cloud technologies, that help speed things up, make it easier to get to that point, and that's what it's all about. So I think it's an area that there'll be more advancements in the coming years. And just to let people know that, they may have a cloud account and don't know all the tools and services that are available in there. Here are some that can be used to great effect, to get data in and out of ArcGIS Online, for example, but lots of other applications too.
So thank you for taking the time with us today to listen to what we've been working on. We're really excited by this. I hope everybody watching this is excited by this. I think it's going to be a really powerful workflow. If you want to learn more, I believe this slide deck will be made available after the Developer Summit. We have a Medium article, well, a series of Medium articles that will step you through a basic version of this workflow. And if you'd like to reach out and contact either Rob or myself, our emails are here on this slide. Feel free to reach out. We love to talk shop, and we really enjoy this type of work.
Thank you very much. Great stuff.
Thanks, everyone.